In this lesson, we're going to talk about optimization. Optimization is the process of optimizing a mathematical quantity, and this is used more for real life applications. For example, you want to minimize the use of resources, or you want to optimize the profit that a company gains. So this process of optimization, it can be done using the first and second derivative tests, and we're going to go through a few examples of how to do this process in this lesson. Now let's talk about some steps for optimization. The first thing I would like you to do when solving a problem of optimization is to understand the problem. You need to identify what is the unknown, what are the given quantities, and what are the given conditions. They are going to give you a bunch of information, and you need to be able to discern which information is relevant and which one is not. After you have understood the problem and read the question in full detail, I would suggest that you draw a diagram. The diagram is going to be very useful to identify relations and to keep track of all the quantities that you know and the ones that you need to find. Then use symbols to give names to each of the quantities that you are going to work with, especially the ones that you know you are going to be maximizing and the variable that you are maximizing against. For example, try to keep letters that make sense for the name of the quantity. A for area, H for height, T for time, etc. Then you should try to find expressions in symbols. So this is the part where you're going to use everything you have known already about the problem and the situation to build relations or functions that you can work with mathematically. And then you would want to take that relation that you found in the previous step, and usually this relation is going to involve two or more variables. In that case, you should try to simplify that expression so that it's only dependent on one variable. And lastly, you will want to use the methods of the first derivative test or the second derivative test to find the absolute maximum or minimum values for the function in the domain that you are working with. Now let's see this process in action for two different examples. Jack makes an open container in the shape of a cuboid with square base as shown in the following diagram. The container has base length x and height y meters. The volume is 32 cubic meters. Let A be the outside surface area of the container. A. Show that the surface area of the container is 128 over x plus x squared. B. Find the derivative of A. C. Given that the outside surface is a minimum, find the base length of the container. And D. Jack coats the outside of the container with waterproof resin. A can of resin covers a surface area of 5 meters squared and costs $15. Find the total cost of the cans needed to coat the container. So we're going to start by finding the area of the container, and we need to keep in mind that since it is an open container, that means it doesn't have the top lid. So what we have to do is find the area of each of these faces and then multiply it by 4 because we have 4 faces, and then add it to the base. So the area is going to be A of x equals 4 times the area of the sides, x times y, plus 1 time the area of the base, x squared. However, this formula is done in terms of two variables, x and y, and we need to try to keep our function in terms of only one variable. they provide this information. The volume is 32 cubic meters. What is that for? That is what we're going to call the ligature of the problem. And that is an expression that is going to help us substitute or reduce our problem of two variables into a problem of one variable. So we know the volume is 32 cubic meters, and that should be x times y. So yx squared should be equal to 32, which means that y is going to be 32 divided by x squared. Now we're going to substitute that back into the area. So area is equal to 4 times x times 32 over x squared plus x squared. And now we're going to simplify this expression. Area of x is 128 over x plus x squared. And this is the final answer for A. Now B was find the derivative of A. So B is A dash of x, and the derivative of that with respect to x is minus 128 over x squared plus 2x. For C, we need to find the base length of the container given that the outside surface area is a minimum. So because we know it is a minimum, that is a turning point, the value of the length of the container should be a critical value. So that means the derivative at that value, let's say x sub 0, should be equal to 0. So when I substitute minus 128 over x 0 squared plus 2x 0, and I make that equal to 0, I should find which is the length that minimizes the surface area. So I'm going to multiply everything by x sub 0 squared, and I get minus 128 plus 2x sub 0 power 3 equals to 0. Solving for x sub 0, this is 128 divided by 2, and then this is equal to 64, and x 0 would be the cubic root of 64. That means x sub 0 would be equal to 4. And the units should be meters. Finally, for D, Jack coats the outside of the container with waterproof resin. A can of resin covers a surface area of 5 meters squared and costs 15. Find the total cost of the cans needed to coat the container. So this is saying that we need to find the total surface area and see what's the cost of coating that much area. So let's find the total area. So the total area when x is equal to 4 is going to be 4 times 4 times 32 over 4 squared plus 4 squared. That is the same as 48 meters squared. And since 5 meters squared costs 15, we need to divide 48 meters squared into sections of 5 meters squared, and then multiply that by the cost, that is $15, and that is $144. The final example, let f of x equal to 24 minus 2x squared for x in the real numbers. The following diagram shows part of the graph of f and the rectangle OPQR, where r is on the positive x-axis and p is on the y-axis, and q is on the graph of f. Find the coordinates of the point r that gives the maximum area OPQR. So we want to optimize the area of this rectangle. So to start, we need to write down an expression for that area. So A is going to be the segment OR times the segment OP. Now I know that OR is in distance, the x coordinate of R, so I'm going to call that x times OP is going to be the distance from O to P, which happens to be the same distance from R to Q. And that distance from R to Q is given by the function f, evaluated at the x coordinate of R. So OP is going to be f of x. So if I substitute, I get x times 24 minus 2x squared. And our final expression would be 24x minus 2x power 3. Now, in order to find the maximum area, we need to find the critical points for this function. So we want to see for which values of x the derivative will be 0. The derivative of a is 24 minus 6x squared. So 24 minus 6x sub 0 squared would be equal to 0. And solve for x sub 0, we get the square root of 24 over 6 plus or minus. And that is equal to plus or minus 2. Now, because the rectangle OPQR would be exactly the same one if I take the negative coordinate, I'm just going to choose the positive coordinate. So having x sub 0 equal to 2, I can now determine the y coordinate of the point R. And since R is on the x-axis, then its y coordinate should be 0. So my final answer would be the coordinates of R are 2, 0.